So first of all, I would like to thank the organizer for giving me the opportunity to speak here today and present my most recent work at this very nice conference, which I did together with Michele Ciccoli, Sven Grippendorf, who is speaking next, Fernando Quevedo, and Roberto Valandro, who is unfortunately not here. And I will focus on the geometric aspect of this paper, because we heard already one talk by Michele on the model building on these geometries, and Sven will talk again on model building on these geometries. And it's about the search for Calabi-Yaus that have an h1,1 minus unequals 0. So why do we need such Calabi-Yaus that have an h1,1 minus and an Orientifold? Because if we do type 2b model building and we consider SUN gauge groups coming from D7 branes, then we want to have a cycle that is mapped under the Orientifold cycle to another cycle that it is not on top of the original cycle. So we want to have the image not on top of the original cycle. Another reason for such geometries would be the case in which we were interested. So we wanted to have these three branes at singularities, and these singularities should come from shrinking divisors of our Calabi-Yaus, which are then mapped under the Orientifold to each other. And here we have an additional constraint. We don't want to have that the divisors that shrink and give us the singularities on which we place the D3 planes should not intersect the O plane, because otherwise the singularities would sit on the O plane and we would get gauge theory models that would look like the ones that Ben was telling us yesterday. So why do we have h1,1 minus greater equal than 1? So if we want to do a large volume scenario, a stabilization via the large volume scenarios, and have D7 branes on which we have the gauge group, the that for the visible sector in the 4 dimensions, or we have these 3 branes at singularities, we want the clean decoupling of the cycle on which we either wrap the D7 branes or on which shrink and then we put on the D3 branes. So by clean decoupling we mean a shrinking to a point. Shrinking to a point means that the first Chern class of the normal bundle of this divisor has to be strictly negative. So integrated this first Chern class over every effective curve of this divisor S has to be negative. And on a Calabi-Yaus, due to the virtue of the adjunction formula, we know that S has to be del Betze. So for model building, we want to cancel the D7 brane charges. So that means that we need an holomorphic involution. And further, we know that for del Betzes, h2,0 is 0. So that means that these divisors are rigid. They are the only representatives in their class. Yeah? And now we want the mapping that maps S to S prime, but S prime shouldn't be in the class of S prime because these are the only representatives in their class, so they would lie on top of each other. And this is exactly the situation we are not interested in. So, and since this mapping maps S from the class in which it is to another class, this has to be greater equal than 1. So now a short outline of how I will continue. Motivation we had already. The next thing is the search for these manifolds. Then I will present you an example that Sven will afterwards use for model building. And I will conclude with a summary and an outlook. Okay, the search. So first we need the set in which we do the search. Yeah, so we wanted to have a minimal assumption that is that h1, 1 has to be 4. The reason for this is that we need already two different classes for the del Pezzos. So we needed del Pezzos in two different classes that made up for 2, and then we wanted to have some stabilization mechanism like large volume, where we needed a large cycle and a small cycle. So plus 2, that makes up for 4. The next natural step is then 5, yeah, and then we get a lot of Calabi-Yaus that we did not yet analyze. But I mean, we find already interesting examples, but we wanted to have some more examples with more interesting structure as well. And the set in which we search are the Calabi-Yaus that are coming from reflexive lattice polytopes. The reason for this is computational, because here we can use toric geometry to analyze the geometries of these Calabi-Yaus. So as I said, two del Pezzos, a holomorphic involution that interchanges them, and since we were interested in the case with the discrete brain set singularities, we wanted to have these two del Pezzos that are mapped to each other, do not intersect the O-plane, and so they also, I mean, this is equivalent that they do not intersect itself. And to have the stabilization, we wanted to have a further rigid divisor, yeah, on which then the instanton or the non-perturbative effects are coming from. So how do we search for del Pezzos? So first of all, for a divisor to be del Pezzo, it has to fulfill some topological conditions. So the Euler number of the divisor has to be smaller than 12, and the holomorphic Euler number of the divisor has to be 1. And further, as I said already, it has to be positively curved. So C1 of the tangent bundle integrated over every effective curve has to be positive. Technically, unfortunately, we can only access a certain subset of these effective curves, because for higher del Pezzos, usually a lot of the curves of the del Pezzo get trivial in the Calabi-Yaus, and with these toric methods, we can only access curves that are non-trivial in the Calabi-Yaus, and so this gives us only indications for del Pezzo surfaces, and has to be checked in the explicit example. But so far, I don't know any examples where, when we have checked this didn't hold. So an involution, we want to have a mapping, and we know that if we have an homomorphismus on the toric polytope, then we have a homomorphismus on the toric space, and this induces us a homomorphismus on the Calabi-Yaus. And so we are interested in Z2 symmetries of the lattice polytope that map the toric divisors that correspond to these two del Pezzos into each other. So let us go to an example where this perhaps becomes a bit more clear. So let's assume for the moment the two del Pezzos correspond to the coordinate Z1 equals to 0 and Z3 equal to 0. So each of these rays corresponds to a homogeneous coordinate of P1, and well, perhaps I reveal this. So this here are the homogeneous coordinates and the weights to the homogeneous coordinates. So this ray corresponds to Z1, Z2, Z2, Z3, Z4. And now we can have several Z2 symmetries. For instance, this reflection here, where Z1 goes into Z3, or Z2 goes into Z4. But the ones that we are actually then interested in are the ones that leave in this simple example here none of the homogeneous coordinates invariant, that map Z1 into Z2 and Z4 into Z3. Because, so first of all, we see here that the involution that maps Z1 into Z3 does not change the class, because Z1 and Z3 lie in the same Kähler class. So here for this involution H1, 1 minus is 0. But for the involution that changes Z1 and Z2 into Z4 and Z3, we get H1, 1 minus equal 1, because here we really change the Kähler classes. We map this to this and this to this. And so we see here that we get an H1, 1 minus that is not unequal 0. Okay, 5 minutes. So this is the result that we obtain. So in the case of H, 4, we obtain in the end 24 examples that met our constraints. So 2 del Bezzos, they are not intersecting, and the further rigid divisors, and this is split it up for the del Bezzos. In the case of H, 1, 5, we obtained 168, and I mean here we started already from 5,000 examples. So what are the tools that we used in this search? So pulp for analyzing the lattice polytope, its extension Mori for triangulating the lattice polytopes, from this obtaining the fans, the Moricon, and the intersection numbers of the divisors. And for further analysis we also used Sedge, and unfortunately pulp couldn't triangulate all the H1, 1 equals 5 cases, so for triangulational reasons we also had to use Sedge. We, in addition to the checks I showed you already, we looked whether this Calabi-Yaus are K3 fibered, because this might get interesting structures for model building and in the inflationary scenarios. And we only considered favorable Calabi-Yaus that have favorable divisors, so divisors that do not factorize on the Calabi-Yaus. An interesting example that would fit into our class of Calabi-Yaus is this one, but in this case the divisor coming from the blow-up factorizes on the Calabi-Yaus in 3 pieces, and so this, so to say, is not accounted for in our search. Also it would fit into our selection criteria. So, and we checked, as I said already, necessary conditions also here for the K3 fibration. So now the example that afterwards Sven will use. So this is the Calabi-Yaus hypersurface, the weights for the ambient space, the degree of the hypersurface, the SR ideal that specifies the fan. A diagonal basis for this space would be this one. In this diagonal basis the volume form becomes strong Swiss cheese. And the involution is the one where D4 is mapped into D7. As one can see here, this changes the classes. So this goes in this and this and this. So H1, 1 minus for this example is 1. And so the singularities, the singularities are obtained by shrinking these 2 divisors, and the mapping is then the one that is described here. And model building on this you will hear afterwards from Sven. So summary and outlook. So we find already quite some cases. So 21 for H1, 1 equals 4 and 168 for H1, 1 equals 5. And we started already doing model building on these geometries, and Sven will talk on this, and also Michele did. But just to stay tuned, please stay. And we want to continue to these other cases, so to higher cases. But as you see, the numbers of the polytopes grow very fast. And so we have to improve our analysis, especially in terms of speed, because a year only has 3 times 10 to the 7 seconds. And if you just multiply this sum with a factor of 30 that makes up for the triangulations, this is of the same order of magnitude. And the long-term goal would be to make all the computed data easily accessible, so on some website or something. Who knows? So thank you for your attention.
Thank you very much, Christoph. Questions? Huh?
So yeah, for the dead pencils to eventually decide that they are dead pencils, so what did you do? Did you compute the Hodge numbers, or?
Yeah, as I said, we computed the Hodge numbers.
Just these
the positivities,
yeah.
And so in the explicit examples, I mean, when you really have the example in hand, you can do further. I mean, you can massage somehow the equations, the Calabi-Yaus equations, and see whether really the del Bezzo comes out. And this has to be automatized. I mean, I think in principle this should be doable, at least for the cases that are hypersurfaces or toric. One should be able to do this automatically and not by hand. At the moment, for the examples we consider, we do this by hand. Show that really, for instance, in this case, the del Bezzos were P2, so dp zeros. So that's very simple. But yeah, for other cases, there's still some work to do.
How did you tackle this large volume form problem with the diagonalization of the intersection form?
I mean, in this case, we weren't really interested in the diagonal form, but yeah. So since we shrink two of these cycles, in the case of h1, 1 = 4, we in the end only have two remaining cycles, and as Benjamin told us yesterday, this always can be brought to large volume form. But the only thing that was interesting for us is that this additional or remaining small cycle is rigid, so that we can get some non-perturbative corrections from this cycle. And this, sorry, I forgot, this rigid cycle should not intersect the two other del Bezzos. So that the singularities in the end are not on the non-perturbative cycle, because the shrinking is such that also the intersection curve has to shrink, and in the end, if these two del Bezzos will intersect the one that is from which the non-perturbative effects come, the singularities would be on the non-perturbative effect. Yeah.
That's question.
Just a technical question. So you used a combination of PALP and SAGE. Could you maybe comment on what one is doing that the other isn't, and vice versa?
Yeah, as I said, I mean, most of the cases PALP can triangulate. Yeah, so for h1, 1 = 4, there's no problem at all. But for h1, 1 = 5, there are a lot of cases PALP cannot triangulate. So for this we use SAGE, or implicitly SAGE uses TOPCon to triangulate, and this we can put then again into PALP, because the new PALP release allows now for having an input of triangulations.
Yeah.
And from this we go back into SAGE and do the analyzation.
And so PALP can do intersections and Morricones and all.
Yeah, of the ambient space, and then calculates the intersection on the. Yeah.
Cool.
Can I make a quick comment?
Yeah.
So in TOPCon, when you try to do h11 bigger than 6, 7 very often empirically, it runs for months.
Yeah. I can expect. I mean, this in the case of 5, you have usually more than 20 triangulations, and it goes up to hundreds. And I mean, one can expect that for h bigger than.
The number of triangulations grow very quick, and the computing time grows almost exponentially, I think. So
Yeah.
That's about every.
Okay, let's thank Christoph again.